A transformer consists of a two set of coil. We call it primary and secondary. These two sets of coil, they are not physically connected, but the energy can transfer from the primary to the secondary through magnetic field. So you will find all the transformer, you have another part we call the iron core. Now the iron core is used to guide the magnetic field from the primary to the secondary part of the coils. If not specified, we can always assume a transformer is ideal. Now we have a voltage, and this voltage has to be AC. So V primary, and on the secondary side of the coil, we have V as the voltage of secondary. Now these two voltage, it can be the maximum voltage or the root mean square value. They are exactly the same, but as long as you use the maximum, you have to make sure you always keep consistent, use the maximum value, or if you choose the root mean square value, just keep it consistent. So the basic theory say, as long as this is ideal, it means there's no energy lost during the coupling from the primary to the secondary. The voltage on the secondary side over the voltage of the primary side is equal to the number of turns of the coil on the secondary side over the number of turns of coil on the primary side. So this is the basic equation. Now in this question, we are given the primary coil has 1,500 turns, and the secondary side, it has 250 turns. Now if you look at the ratio, you can see the ratio, you can see the number of turns in the secondary coil is less than the number of turns in the primary coil. It means the voltage will step down. So let's plug the number into the equation. Now you rearrange the equation. So the voltage on the secondary side, if you measure this one, you will find this is equal to 38.3 volts. Now because we are using root mean square value, so the 38.3 is the root mean square. You are better specify, I put a bracket at the end of the unit so people know you are using the root mean square value. Next, we are looking at what is the current. Now this time we have to ask what it really means a ideal transformer. An ideal transformer means the input power is equal to the output power. Now you may find now the voltage step down. This particular transformer step down the voltage, reduce the voltage. Does it mean it lose the energy? But if you think about it, not necessary, because the power, the energy per second is actually equal to IV. So the voltage reduces, but at the same time, the current flowing through in the secondary coil will increase. Therefore, the power is equal. So we have IP, VP, and the output power is equal to IS, VS. So assume this is ideal, so we can say IP, VP, the input power or the power on the primary side is equal to the output power, which is IS, VS. Okay, so the rest is just mathematics. So we are saying is now the IP is equal to Vs over Vp, Is, and you just plug the numbers in, and you will get 38.3 over 330 times 2, and then you got 0.333 ampere. So what I mean, let's look at what this transformer, what this question tells us. If the primary coil, it has 1,500 turns, and the secondary has 250 turns. Now, before we can do anything, we know just from the number of the coil, we know this transformer will step down the voltage. Now you may ask, how about if we reverse? If we reverse, it will step up. So it doesn't matter which one is primary, which one is secondary. The name primary and secondary is how we use the transformer. It's not something inherent in the transformer. And now the input voltage is 230 volt would mean square, and from the ratio now we know the output voltage is 38.3 volt would mean square, and we also know the output current is 2 ampere. So again we use the ratio, and we can say now the input current must be 0.333 ampere. So you can see now the voltage step down, reduced from 230 to 38.3, but the current increases from 0.333 ampere to 2.0 ampere. So for the ideal transformer, there's no energy lost. Again, we assume this transformer is ideal. In this particular question, this ideal transformer steps up the voltage from 120 volt to 1200 volt. So VP is 120 volt, and VS, the voltage across the secondary coil, is equal to 1200 volt. Now, part 1, it asks you find the turns ratio. So we just use the proportional idea. It means Vs over Vp equal to Ns over Np, and is equal to 1200 volt over 120 volt. So the ratio is 10 to 1. Next, it asks what's the current on the secondary coil. So because this transformer is ideal, so we can assume the power in is equal to the power out. So current of the primary current multiply the primary voltage equal to the secondary current multiply the secondary voltage. And we know now Is is equal to Vp over Vs multiply Ip. Okay. So we have 120 over 1200 and multiply 1 ampere. And this is 1 over 10 multiply 1. So the answer is 0.10 ampere. A transformer has primary turns Np equal to 800 and the secondary turns Ns equal to 200. Now the primary, it has voltage of 240 volt RMS. So what is the voltage on the secondary side? So we use the proportional argument again. So Vs over Vp equal to Ns over Np. So this is equal to 200 over 800. So it's a 1/4. So the voltage of the secondary side voltage is 1/4 of the primary side. So you can see, because the number of turns on the secondary side is less than the number of turns in the primary side, so this transformer steps down the voltage, and which is equal to 60 volt RMS. Number B, if a 20 ohm resistor is connected across the secondary side, so what is the current? So we can use Ohm's law on the secondary side. So it means Vs equal to ISR, and Is equal to Vs over R. 60 over 20 equal to 3 ampere. Assuming the transformer is ideal, so the input power is equal to the output power, or the power on the primary side is equal to the power of the secondary side. So we can say IP Vp equal to Is Vs. So IP is equal to Vs over Vp multiply Is, and this is equal to 60 over 240 times 3, and it is equal to 0.75 ampere. Part D, it asks you explain physically what ideal transformer means in the context of energy transfer. So ideal transformer is the sort of transformer energy on the primary side, or the input power, is equal to the power of the output, or the power of the primary side equal to the power delivered to the secondary side. Now, there's a 3 basic criteria, and there's a 3 common way energy will lose. So the first is the energy may lose because when the current passing through all the wire, it will create heat because the wire carry resistance. So it means there will be energy loss due to the wire. So sometimes we call copper losses, and this is the heating effect. Number 2, the energy is transferred from the primary side to the secondary side through the changing of magnetic field. So if we look at the primary side, when the alternating current change, it also changed the magnetic field through the iron core, and this magnetic field change of the magnetic field will cause electromagnetic induction, and this is how the voltage across the secondary side appears. Now the issue is when the magnetic field change within the iron core, it will also induce the flow of current. So if we look at the cross section of the iron core, this part here, when the magnetic field change, it will create a current flow across the iron core, and this current flow will create a lot of heat. Therefore it will cause energy loss, and this current flow within the iron core, this one, we call this static current, and it will definitely cause some energy loss. So So second possibility is called the core losses and mainly added current. The third part is why people use iron core, because we hope to channel all the magnetic field coming from the primary side to the secondary side. But in reality, some of the magnetic field may leak outside. So this leaking magnetic field will not have any effect of the secondary side. It means we cannot couple all the energy through magnetic field from the primary to the secondary. So the third reason it may lose energy is the leaking or the leakage of magnetic field, or technically we call magnetic flux. Okay. Now all these three, if there's no energy loss on the copper wire, no energy loss due to the eddy current flowing through the iron core, if no energy loss due to the leakage of magnetic flux, then we will say the power from the primary side will 100% transfer to the power of secondary side. It means this is what it called ideal. A AC voltage can turn into a DC voltage through a rectifier. The main component of a rectifier is called diode. This is the symbol of diode. And you can see this when the current passing through from this side is allowed. However, the diode here, this bar here, means it will block any current passing through from the opposite side. When the voltage is high, for example here, it means this side of the diode is a high voltage and this side is negative. The current can pass through, so this one will pass through, and the same as this part. However, when we have reversed the voltage, it means if we have a positive here and negative here, this one here, the diode will block the current. Therefore, no negative voltage will be measured across the load resistor. A diode can be made from different materials, but most commonly it's made from semiconductor, silicon. And let's now look at how the current and the voltage relationship between a diode. Remember, diode is different from a resistor. Let's recall what happens if you have a voltage across a resistor. And if you measure the voltage and if you measure the current. Now, first assume this is DC. Things are a little bit simple, and you can plot V versus I, and the slope here is your resistance because V equal to IR. So this is your slope. Now if you plot I versus V, and in this case you have to rearrange the equation, and this is I equal to 1 over R V, so the slope is 1 over R in this case. Now, however, if you look at the current against the voltage across a diode, it's not a linear curve like the resistor. So this is a non-linear characteristic. Let's look at about how it behaves. If you put a positive here and you start increasing the voltage, and you will find there's a no current flow here. Remember, the inverse of the slope tells you the resistance. So there's a no current passing through. It means you can imagine like a infinity resistance. Now, once you start increase the voltage, you start measuring current passing through. So you can start imagine you have a current meter here, and you also providing a voltage across. So it start passing through, and once it reach this one, you have as much as current you like. So if you look at this part here, this means the resistance here is nearly zero. So it's like a perfect conductor. So this voltage is important because after this voltage, the diode become a perfect conductor. And this voltage is called the forward voltage drop. And if you look at the table here, silicon, the forward voltage drop is roughly equal to 0.7 volt. So it means you have to apply a forward voltage bigger than 0.7 volt in order to passing through the current. So this is 0.7 volt for silicon. Now, if we reverse the voltage across the diode, it means if we have a diode here, we put this is positive and negative. And you can see here, there's a nearly no current through that. For the ideal diode, it should be 0. But we have to say here, in the real diode, there will be a very small current here. But this is very small in the 10 to the minus 6 ampere order of magnitude. So we call this one neat current. And in any practical sense, you can assume this is 0. However, if you keep increasing the reverse, we call the reverse bias. So if you increase it to about 70 to 100 volt, you will suddenly find there's a huge current on the passing through the negative side, and this is called the breakdown voltage. It means once you're passing through this voltage, the diode cannot block any current through. It will become like a conductor. So this range here is about 70 to 100 volt for silicon. So part B, determine the peak output voltage. Now, if the input voltage here is 12 volt, but remember you lead 0.7 volt as the forward voltage drop. So this one cannot be 12 volt. So the peak voltage here, this VP, the output peak voltage, the peak here, the output is equal to 12 minus the forward voltage drop. The forward voltage drop is 0.7 for silicon, and therefore it's equal to 11.3 volt. So you only get 11.3 volt here if your input voltage is 12 volt. Next, how to find the FHDC output voltage. It means if you look at the total power here, this is your power. Can you find the DC equivalent? I want to have a DC voltage which will deliver the same power of this voltage. Now remember, this is a DC, but this DC voltage still fluctuating. It means it starts from 0 to the peak, and the peak we just know is 11.3 volt, and go back to the 0, and then stay for the 0 for a while, and increases again to 11.3 volt. And the area here it tells you the power. So we want to find the really true DC voltage such that it will produce the same FH power as these two. So the formula which will be given in any exam or test is equal to VDC equal to the peak output voltage over pi, and this is 11.3 divided by pi equal to 3.60 volt. In this question, we first have to sketch the voltage at each stage so we can understand what to do and include all the known parameters in the sketches. The AC input signal, and this is the AC input signal. And after the transformer, the voltage will drop. So this is the voltage, or the AC voltage after the transformer. The voltage will pass through a half-wave bridge rectifier. So it means the voltage after the rectifier will look like this. 1, 2, or one more. And at this stage, if you put a capacitor in parallel to the load, you will get a voltage like this. Now, I will first use dotted to represent this one here before the smoothing. And then after smoothing, it charge, and then it will drop to here, charge, and then it will at the peak drop to here, it charge up and drop. So let's define all the quantity on these sketches. So this circuit want to supply a DC voltage of 22 volt. This is the FH DC voltage. So we should put this one here, the FH value. And this value is 22 volt. Peak to peak ripple, which is 4 volt. So this now, if we measure from here to here, the peak to peak here is 4 volt. This is the peak to peak voltage of the ripple to a load resistance, which is 5k ohm. So this is important. Now the AC input is 240. Peak value is the maximum in 50 Hertz. So this one is 240 and the frequency is 50 Hertz. This question is assume the transformer and the diode is ideal. It means there's no energy loss in the transformer, and also there's no forward voltage drop across the diode, so we can ignore these two factors. A, what is the load current? So the load current, we can say we have a voltage. This is output voltage. This is 22 volt. This is the FH DC voltage, and it has a load resistance of 5k. So RL is 5k ohm. So this is the I. So the I load is equal to 22 over 5k ohm. It equals to 4.4 milliamp. Next, what is the turn ratio of the transformer? Okay, so now we need to find is the peak voltage of this DC. This DC is the DC after the rectifier, but it's still not smoothed. So we call this V peak. Our next question is how to relate the VDC, in this case 22 volt, which is the average DC voltage after smoothing, to the peak voltage before smoothing. Now you may remember there's a formula. It say the VDC is equal to V peak over pi for the half wave rectifier, but we cannot use this formula because this VDC in this formula is this voltage. However, once we put the capacitor in parallel to the load, everything will change. The VDC calculate in this part, and the VDC we found from here, which is 22 volt, will be substantially different. And this VDC will be a lot larger than the value we calculate from here. So what it means is, this time we have to use this property. Remember, it is given that the peak-to-peak voltage is equal to 4 volt. So if we look at the graph, it means this is 4 volt. And if the voltage between here and here is 22 volt, so the peak value here is, it means if we measure this voltage here, it will be equal to 22 volt plus 4 volt divided by 2. So it must be equal to 24 volts. So this is a very important step and you may get confused. So what I mean is, the peak voltage here, from here to here, before the voltage is smooth, this we call the V peak, is equal to 22 volt plus half the ripple voltage, and in this case is equal to 24 volt. This voltage here is also equal to 24 volt, and the input voltage is 240. Now what is the ratio of the turns? So we can say NS over NP equal to VS over VP and equal to 24 over 240. So it's a 1:10 ratio. For the ripple voltage, we have a formula. It's a V ripple. Remember, this is P to P. Is equal to the load current over FC. This is for half wave rectifying, and C equal to I load, of course, V ripple, and this is frequency, and the load current is equal to 4.4 times 10 to the minus 3, and the voltage is 4 volt, and the frequency is 50. So the answer is 22 microfarad. So this is the transformer. This is the dial. This is the capacitor used to smooth the output. This is 240 volt, 24 volt. This is NP, this is NS. So NP over NS equal to 10 to 1. this value, the capacitor used is 22 microfarad, and the load resistance is 5k ohm. Now let's look at how the signal at each stage, and it requires to supply 10 volts with the peak-to-peak ripple of 2 volts, and the load is 1k ohm. So we can say at the final stage, now remember this is a full wave, so this is the AC, and this is after the transformer, and after the rectifier we have this, and this is charge up, discharge, charge up, discharge, charge up, discharge, and this is the FH, and this is the V node, or sometimes we call the VDC. Now the peak to peak ripple is equal to 2 volts. So this here is 2 volts, and the low voltage is 10 volts. So this is 10 volts. So first let's calculate the load current. The load current is the low voltage over the low resistance, and this is equal to 10 over 1000, equal to 0.01 ampere. So let's put it here. So IL equal to 0.00. So the IL equal to 0.01 ampere. Next, we want to find the voltage at this point. Okay, so we can call this VDC this time, or we call it V peak. So the low voltage is 10 volts. And the peak here is 10 plus 1. So B, the voltage, peak voltage is 10 volt plus the ripple voltage, 2 volt divided by 2, so is 11 volt. So this is 11 volt, and of course it means this 11 volt. The input voltage is 220 volt. So the transformer, the ratio, so C is the V secondary, V primary equal to NS, NP, and this is equal to 11 over 220. and this is equal to 1/20, the ratio. What is the value of smoothing capacitor? Now, this time again we use V ripple P to peak equal to the load current. Now this time, because this is a full width, so we have to 2 times 50. So this is the frequency, 50. And this is C. And from here, we can say C is equal to 0.01, 2 times 50 times 2, and equal to 50 microfarad. So this is our circuit. This is the transformer. So this is the full width rectifying arrangement of the diode. And this is the smoothing capacitor, and this is the load.